Hi, I'm Harshit, and this is a presentation of our work, Dual Reinforcement Learning. Off-policy RL, despite its promises of handling arbitrary quality of data and learning a good policy, fails to make use of expert trajectories when they are added to the replay buffer. Instead, the value function explodes and becomes unstable. The heart of the issue lies at using off-policy RL in the deadly setup of function approximation plus bootstrapping, which can cause instability. On-policy policy gradient approaches are generally more stable. What if we could obtain on-policy policy gradients using off-policy data? Prior approaches have not resulted in performant practical algorithms, and this is what we seek to remedy using dual RL and dice approaches. Some preliminaries. The state action visitation is the discounted probability of reaching a particular state and action in the environment. We denote the offline data visitation by DO, expert data visitation by DE, and replay buffer visitation by DR. The F divergence is a measure of distance between two distributions where f is a convex function and f star denotes the convex conjugate of function f. For ease of notation later in the talk, we denote the q backup operator to be the reward plus expected next q and the v backup to be the reward plus expected next v. Consider a standard regularized objective where we are trying to maximize the reward function but constrained to some offline data distribution. We can rewrite this objective as the following two convex programs. This is done by formulating the RL objective in terms of arbitrary variable d, and later constraining it to be a valid visitation distribution using Bellman flow constraints. Both forms of constraint guarantee the optimal policy. Taking the primal Q objective from the previous slide, we can convert it into an unconstrained dual objective. Both objectives have the same optimal solution as strong duality holds. Note that the dual objective is completely off policy and has a actocratic flavor along with some of the benefits listed below in the slide. Now, an even more interesting transformation is the result of taking dual for the primal V problem. We obtain an objective for reinforcement learning that can learn without a two-player actor-critic game. Our first realization is dual RL clear up the landscape of different approaches in RL. These approaches have been developed using widely different derivations, and we show in the paper that they are essentially the same approach under the lens of dual RL. Our hope is that this unification allows the researchers to analyze a number of RL algorithms and with a common foundation, and for practitioners to carry over the design choices across methods that are instantiated with the same setup. Recently, the pessimistic value functions and implicit maximization methods have dominated the class of performant offline RL algorithms. Pessimistic value function promise a lower bound on Q function, whereas implicit maximization select actions within the observed actions to maximize the Q values and have been motivated as roughly support regularization methods for offline RL. But it is not clear how these two classes of methods relate to regularized RL or if there is any connection at all. Dual RL helps us connect the dots. We show that existing pessimistic value function algorithms are dual Q methods and existing implicit maximization algorithms are dual V methods. Eventually, they are all really solving towards the same solution using different objectives. We can now see why the unification is important. A recent method, extreme Q learning, was derived by replacing the Gaussian distribution assumption on Bellman errors with a Gumbel distribution. As we unify these algorithms, it becomes immediately clear that XQL is a dual V algorithm for solving offline RL, where the F divergence is the reverse scale divergence, and therefore the F star is exponential. Exponential function causes exploding gradients, and this explains the instability of XQL, which was pointed out by the authors and required some fixes. We can fix this instability using a divergence whose F star is a low-ordered polynomial. We observe across-the-board improvements with these algorithms using TV and chi-square divergence, and we call the family of algorithms dual V learning. Interestingly, from the perspective of dual RL, there is not really any difference between imitation and reinforcement learning. Simply setting the reward function to 0 gives us the imitation learning objective, and all previous derived methods follow again with reward function equal to 0. We can see that some recent algorithms, notably implicit behavior cloning and IQLN, are just dual methods in disguise. A limitation of existing imitation methods is their inability to handle off-policy data. We should be able to handle the more practical situation where we have a large amount of possibly suboptimal data and a few expert demonstrations. This offline dataset is a rich source of information about the dynamics of the environment and should be used to do better imitation learning. Prior methods either create lower bounds to the imitation learning objective and or use other ways to leverage offline data. We propose to use the following mixture distribution matching objective. First, it is a valid imitation learning objective as it is only minimized when the visitation of agent matches that of the expert. We don't require any restrictive assumptions on coverage, lower bounds, or even a discriminator to train the imitation learning method. Using similar primal dual reductions, we obtain the dual objective for mixture distribution matching. This objective samples from only the offline and the expert data to solve the imitation learning problem. In fact, the method's intuition becomes clear when we instantiate recoil with the chi-square divergence. The objective aims to increase Q at the expert transitions and decrease the Q at policy transitions, all this while trying to maintain Bellman consistency with a zero reward. The Bellman consistency is necessary to propagate information of how to recover to expert states. Recoil outperforms baselines by a wide margin, especially when there are few expert samples or in a high-dimensional task where the discriminator easily overfits. This slide visually compares the different methods and shows that prior methods are unable to recover after making a mistake. Moreover, recoil is an inverse RL method and can be used to recover expert's reward function. In general, we have a greater set of algorithms we unify. We direct you to the paper for more information. Thank you for listening to the talk. Please check out the website and email me if you have further questions.